What's up guys, welcome back to Agora Math Circle's Mathcounts training. This is session 4 of our 12-part series. This is a continuation of what we learned in session 1, 2, and 3. So go check out those videos if you haven't already. My name is Mugil Shanmugam, and I'll be presenting this series of videos. Okay, so let's get right into it. So session 4 topics. What exactly are we going to be learning today? So today we will be covering the following: Pythagorean triples, cutting regions, counting triangles, and counting rectangles as squares. As the name might suggest, today we're going to be going very deep into possibilities, or like how many possibilities are there of this happening? How many possibilities are there when you have this plane cut by this many lines? So it's going to be relying heavily on combinations, so we'll be reviewing those too. And we have some subtopics today before we go straight into the main content. So our subtopics in Pythagorean triples, we're going to have common triples and some problems. In cutting regions, we're going to learn how to visualize them very basically, and then some problems. In counting triangles, counting rectangles, and counting squares, we're going to go over some basic techniques that you can use and some problems. Alright guys, so let's start. So Pythagorean triples. Most of you probably know the Pythagorean theorem, which is a squared plus b squared is equal to c squared. And this applies for a right triangle where a is one leg, b is one leg, and c is your hypotenuse. So leg squared plus leg squared is equal to hypotenuse squared. This is very useful when you want to find the hypotenuse, when you want to find the leg, and you have the other information. Now, there are certain common a, b, and c values, or leg, and hypotenuse values, that when you see, you should automatically be able to recognize that it's a triple and find the rest of the values. So these are 3, 4, and 5 right here, 5, 12, and 13, 7, 24, 25, 8, 15, 17, 9, 40, 41, and 35, 12, 37. So these are very just common values. So when you see that maybe you see one leg is 3 and one leg is 4, you should automatically know that the hypotenuse is 5. They're just very common values you'll see a lot. But we also have figured out that we can use these to create some basic formulas. So one formula is 3n, 4n, and 5n. So basically, if we take any triple that we already know and multiply it by the same number, so in this case n, a common number n, then we can make a new triple that's bigger in value. So 3, 4, and 5, I can multiply everything by 2 and get 6, 8, and 10 to get a new triple. So in that way, we can multiply everything by a common number and get new triples. So that's just something handy that you can use once you know these base triples. Okay, I'm going to stay here for a second if you want to take a quick screenshot of the triples. But after that, let's move on. Okay, so a Pythagorean triple can be written in the following form: x, m plus n over 2, and m minus n over 2, where x squared is equal to m times n. So this only holds true if certain conditions are met. 1, m should not be equal to n. 2, m has the same parity as n. That's just basically a super fancy way to say that m is even if n is even. So same parity means the same odd or even value. So 2 and 4, they would have the same parity because they're both even. Or 3 and 5, they would have the same parity because they're both odd, and so on. And m greater than n. This is just some conditions that you need to meet if you want this formula to apply. X, m plus n over 2, m minus n over 2. If you want this to be a triple where x squared is equal to m times n, then you need to make sure that these conditions are met. Now, sometimes you'll be given one leg, not two legs, just a single one leg with the value x. Let's just say that the value is like 3 or something. But for now, we're just going to assume it's x, right? And they'll ask you how many Pythagorean triples are possible with this value. So what you need to do is first you need to evaluate what condition x falls under. And once you find that out, then you can use a formula. So if x is prime, then there's only one Pythagorean triple or set of values. So again, a prime number only has two factors, itself and 1. So if a number, or your leg basically here, is prime, then there's only one Pythagorean triple possible for that triangle. But if your number is odd, then you can use the below formula that I'm about to teach you without the O value. And finally, if x is an even composite number. So composite number has 1 and itself has factors, but it also has other factors other than that. So an even composite number would be any even number other than 2. And in this even number, or if you're given this even composite number x, then you could find t and o. t is the number of factors of x squared. So again, you know what x is. If you square that, the total number of factors, that's going to be your t. And O is going to be the number of odd factors out of these total factors. Then you can use the following formula. N, capital N. Capital N simply means a number of something. So here it represents the number of triples, is equal to the floor function of t over 2 minus O. So again, the floor function, we went over this in like session 3. So the floor function basically means take the integer that's smaller than it. So 2.5 floor function would be 2 because that's the smallest integer, but it's like the biggest integer that's smaller than the number that you're given. And again, for x is equal to odd, so if x is odd, maybe like 3, 5, 7, 7, 9, then what you would do is you would simply do this formula, but you don't have to calculate O because your number is already odd. There's no need to find odd factors. Okay, so let's move on to the next slide. So here we have a sample problem utilizing the formulas that we just learned. So find the number of Pythagorean triples for a right triangle if one leg is 15 units long. So your 15 units can be your x value if you want to think of it like that. And this is from the Mathcounts handbook in 2007 to 2008. Okay guys, so pause the video here, take a quick break, and try to solve this problem on paper, and then I'll go into how you can solve it. So pause the video here. Okay, so hopefully you guys paused and solved the problem. Let's get back right into it. Okay, so first we need to calculate, is 15 odd, is it even, or is it prime? Okay, so 15 isn't prime because its factors are 3, 5, 1, 15. So it obviously is not prime. And it's odd because it's not divisible by 2. So we know that our formula is going to be n is equal to the floor function of t over 2. And t is equal to the number of total factors of x squared. So that's one way we can do it. And this one is pretty self-explanatory. Simply just plug in the number and find the floor function. Pretty simple. But instead of using this formula, we can also solve it using another method. Remember that we learned that the factors, or not the factors, sorry, you can represent a triple as the following: x, m plus n over 2, and m minus n over 2. So we can try to represent it as that, and then try to find the different triples that you can form using that. So remember, back then we learned that x is equal to m squared. X squared is equal to mn. You can see it right here. X squared is equal to mn, and you have our triple written in this form. So based on that, what we can do is we can simply write out our number in that form. So x squared is equal to mn, and our x squared is going to be 225 because that's 15 times 15. So then we can find the different m's and n's that are possible. M can be 225 and n can be 1. M can be 75 and n can be 3. M can be 45 and n can be 5. M can be 25 and can equal 9. And m can equal 15 and can equal 15. But this one doesn't apply because m cannot equal n. Remember back here it says m is not equal to n. And that's also the reason why we're not doing n equal, so that's also the reason why we're not doing n equal to 1, m equal to 25. We're not flipping each and every one of those combinations we just came up with because then it would violate the condition m is greater than n. Okay, so if we go back here, as you can see, our answer is going to be 4 Pythagorean triples because we have 4 different combinations of m and n that satisfy our conditions, so we're going to have 4 triples. Okay, so let's move on to the next slide. So now let's just go over what exactly combinations are. I went over this in the previous video, but I'm just going to review it real quick here because we're going to be using combinations a lot in today's video, and you want to know how to use the formula. So when you see something like this, x is equal to 10 over 2 in like a weird fraction form and some parentheses, this means 10 choose 2. You're doing a combination. Out of these 10 objects you have, you're thinking of the number of ways it's possible to get 2 objects out of these 10. So 10 choose 2. And to calculate that, it's going to be 10 factorial over 2 factorial times 10 factorial minus 2 factorial. Sorry, 10 minus 2 factorial, which is 10 factorial over 2 factorial times 8 factorial, which is 45. And as you can see, I basically just broke it down into factorials. And factorials is going to be, if it's like 3 factorial, it's going to be 3 times 2 times 1, and so on. So here is the formula. So if you're going to do n choose r, you can do n factorial over r factorial into n minus r factorial, and that's how you're going to calculate your n choose r. So whenever you see a combination in today's video, maybe it'll be like n choose 4, then you can just plug it into this formula and you'll be able to solve it. It might take a little time initially, but it'll be worth it at the end. So in case you want to screenshot the formula real quick, I'll stay on the slide for a few seconds. Okay, so let's move on to the next slide. So now we can get into cutting regions. So we need some basic knowledge for cutting regions so we can actually utilize this. So the basic knowledge that we need at the beginning is if there's n points in a plane, the maximum number of lines connecting these points is n is equal to n choose 2. So there we go. We got our first combination of the day. So for this one, you'd simply plug it into that formula we just learned. So it'd be n factorial over 2 factorial, n minus 2 factorial. So for now, we can't calculate it because we have a variable, but when you find out what n is, it's simple, pretty easy to calculate. And again, n is the number of points in a plane. So if I had 10 points in a plane, it's pretty easy to calculate. It'd be right here. 10 choose 2, 10 factorial over 2 factorial into 10 minus 2 factorial. You can calculate that out to be 45. So that's how you would solve this basic thing that asks, if I have this many points in a plane, how many lines connect those lines? Those points. Now, the maximum number of triangles that connect these points is going to be n is equal to n choose 3. Again, plug into the combination formula once you find out what little n is equal to. And the number of intersection points of these lines. So again, remember, if we have these n points and we've created these lines that intersect them using this formula, n choose 2, then we can find the number of intersection points of this. And that's going to be 3 into n choose 4 plus n. You can also write it as n choose 4, 4 choose 2 over 2. So that's just some basic formulas, and all this is operating on the premise that you have these basic n dots, so n number of dots in this plane, and you're going to connect them using triangles, lines, intersection lines, so on. Okay, so let's move on to the next slide in about 2 seconds. Okay, so now we're going to learn some more complex formulas using cutting regions, because those are pretty basic and it's a very basic situation. You're just given some points and they're asking you to connect them. Now, if you're given an n-gon, so n-gon sometimes confuses people. It's basically referring to a polygon. An n-gon means that a shape with amount of sides. So an n-gon, I could change that to a 13-gon. That would mean that I have a polygon with 13 sides. So n-gon is simply just a representative for how many of sides you have. Little n is going to be equal to the number of sides you have. And big N, as I told you guys many times before, it's going to be the number of things. So the number of ways, the number of diagonals, the number of intersection points. It's simply just the number of something. So big N is equal to n choose 2 minus n, which is also equal to n into n minus 3 over 2. So personally, I'd probably choose to remember the easier one, which is n into n minus 3 over 2, because that's easier to calculate than doing all the factorials and stuff. So it's just up to you, personal preference. Remember whichever one is easier for you to remember. And this is the number of diagonals of a convex n-gon. So it's a closed polygon with n sides. Now, the number of intersection points of these diagonals. Okay, so now these formulas are basically just building off each other. Now, we already have our polygon here, and basically we have a bunch of diagonals in it. Well, how many times do these diagonals intersect? Well, to find that, we just do n choose 4. So pretty simple. Now, the number of regions divided by these diagonals. Okay, so now we have all these diagonals that have intersected each other, and they've formed these little regions. So if you have a diagonal here and a diagonal here, there's a region formed in between these diagonals. And that region, to find the number of regions in the total polygon after they've been divided, that's going to be equal to 1 plus n choose 2 minus n plus n choose 4. So again, that's going to be 1 plus n choose 2 minus n plus n choose 4. So these are all just basically formulas you'd apply, but in this case, your situation is you're given an n-gon and you have a bunch of diagonals cutting through it. Okay, so let's move on to the next slide here. So cutting regions, region formulas. So region formulas, when I say that, there's just formulas when I'm given a plane and they're asking me how many regions are formed if I do this. How many regions are formed if there's 5 lines cutting through it? How many regions are formed if there's 4 circles cutting through it? How many regions are formed if there's 4 circles and 5 sides, or 4 circles, and 5 lines. So again, it's just the number of regions you have in this plane. So when your plane is divided by little n lines, so little n, that's just the number of lines here, well, it's going to be m into n plus 1 over 2 plus 1. Again, m into n plus 1 over 2 plus 1. So that's just a way how you calculate it. And again, so into this formula, you just plug in your n, which is the number of lines you have. Now, for a plane divided by n circles, well, and if they ask you how many regions there are, you can just use this formula, n squared minus n plus 2. So again, little n is your number of circles. Now, if you have both, what you would do is your n is equal to the number of circles, and m is equal to your number of lines. So what it would be is n into n minus 1 plus m into m minus 1 over 2 plus 2mn plus m plus 1. So basically, first we just dealt with only lines, then we dealt with circles only, and then we combined them to find if I have this many lines, this many circles, how many regions are going to be formed. And again, you want to keep your variables straight. Usually when n is by itself, it can be lines or circles. So sometimes they'll say n lines or n circles. But when they're together, your m, so it's going to be m lines and n circles. Okay, so now we can do the same thing that we just did with these lines and circles, but we just do it with rectangles and triangles, or even m-gons or n-gons. Again, m-gon or n-gon is just going to be a polygon with a set number of sides. That's going to be represented by your m or your n. Okay, so using n rectangles, so some number of rectangles, well then you can create 2 plus 4n into n minus 1 regions. That's how you calculate how many regions are going to be in this plane. Using n triangles, well that's going to be 2 plus 3n into n minus 1. So as you can see, there's a bit of pattern here. It's about the same, except a rectangle has 4 corners, so you're going to use 4. A triangle has 3 corners, so you're going to use 3. Or you could think of it as a rectangle has 4 sides and a triangle has 3 sides. So that's how they got the formula. Now, if you're using an m-gon, so some number of m-gons, well that's going to be m times n. So m is your number of sides. Your number of sides times n into n minus 1 plus 2. So as you can see, this is just adapted based on the original formula. It's 2 plus m into n, because that's going to be the number of sides times your n into n minus 1. And n is always just going to be your number of something. So here, big N is the number of regions, small n is going to be our number of m-gons. And finally, if we're given chords in a circle, so chords in a circle, they're basically going to be connecting 2 points of the circle. Now, you may confuse these with a radius. A radius connects a center and a point on the circle. A chord connects 2 points on the circle, on the edge of the circle. And if you have n points in the circle, then you're going to calculate it by n choose 4 plus n choose 2 plus 1. And again, if you wanted to calculate n choose 4 and n choose 2, once you knew what little n was, then you could simply just plug it in to our formula. Alright, I'm going to pause here for a second in case you need a little break, if you want to take a screenshot, and then we'll move on. Okay, let's move on. So let's go into a quick sample problem based on our cutting regions. So again, that was a lot of formulas. Just try to remember what you can, and eventually it'll come to you naturally as you continue doing these problems. And then again, here I just want to point something out. If I go back to the other slide, I don't want you guys to memorize the rectangles, triangles, and m-gon formulas, because you can just remember one of these and remember the rest. So if I know the rectangle formula, 2 plus 4n into n minus 1, well then I can just figure everything else out, because it's going to be the same exact formula with the change right here. So right now it's 4n. If it's a triangle, it's going to be 3n, because there's 3 sides in a triangle. If it's an m-gon with m sides, it's going to be mn. So if you remember one formula, you can remember the others. So just try to think of patterns like that that will help you remember them without having to memorize each and every formula. Okay, so here's our problem. What is the maximum number of regions that 5 circles and 1 line can divide a plane into? Okay, so here we use our formula. Remember, you're not going to be using the formula for only lines or only circles. You're going to be using the one for both of them when they're combined. So you just need to plug in your numbers into the formula. Make sure to keep your variables straight. In this case, n is probably going to be your circles, m is going to be your lines. But just make sure to keep your variables straight when you're solving it out. Okay, so pause here, solve the problem. Okay, so hopefully you guys solved the problem and you guys know your answer and how you got it. So let's go into the solution for this one. So we need to use the formula for a plane divided by circles, which is represented by little n, and lines, which is represented by little m. Okay, so as they said here, we have 5 circles and 1 line. So your n is equal to 5 and your m is equal to 1. So now we just need to plug in our numbers into the formula. So it's n into n minus 1 will now become 5 into 5 minus 1, which is 5 times 4, which is 20. M into m minus 1 over 2. Well, that's 1 into 1 minus 1 over 2. I already know that's going to be 0. Plus 2 into mn. Well, 2 into mn is going to be 2 into 1 into 5, which is 10. And plus m, which is 1, plus 1. So that's going to be 2. 20 plus 10 plus 2 is going to be 32. So there are 32 regions into which this plane can be divided at max. So in case I didn't mention it, these formulas are for the maximum number of regions you can divide something into. So there are 32 regions at maximum that you can divide this plane into. Okay guys, so let's move on to our next topic, which is counting triangles. So counting triangles, you've probably seen these problems somewhere or the other where you're given a triangle with a bunch of lines in it and they say, how many triangles are there in this bigger triangle? And sometimes it's usually, most people just go and they start counting with their pencil. 1, 2, 3, 4, 5. But that usually doesn't work because you end up missing a triangle here, missing a triangle there. Always there's some problem. So we have a formula to do that that's probably going to be much quicker. It may not be the quickest thing, but it's probably going to be more accurate than what you're going to be doing with your pencil and just counting each triangle. So given a triangle with multiple lines, there's a possibility of n choose r total triangles, where little n is equal to your number of lines and r is equal to 3, as we can choose any 3 of these lines to make a triangle. So just take a moment to digest all that. There's a possibility of n choose r triangles. Little n is the number of sides, or not the number of sides, sorry, the number of lines that you have in your triangle, and r is equal to 3 because you need to choose any 3 lines. So now we did that. But some people just end here, but that's not going to be right because we need to account for degenerate triangles. So by degenerate triangles, what they mean is there's going to be some triangles that are made of 3 points. All triangles are made of 3 points. But if all of the points are on the same line, you may get a tiny triangle, but it's not actually going to be a triangle because it's going to appear like a line. So we need to subtract all this out. Well, how do we do that? First, we do n choose r again, but this time we need to find n is equal to the number of lines meeting at a point. So take any point in the triangle, of the bigger triangle. So usually triangles have A, B, and C. So maybe choose point B. Count how many lines are intersecting there. Now, once you count that, then you do that number, choose 3, to find the number of degenerate triangles from that point. You do the same thing to the other points that also have lines meeting there, and then you subtract out these values from your total. And we'll do an example, so don't worry about that. Just try to get these formulas down and how you would apply them. So again, what we do is we find the total number of triangles, and then we subtract our degenerate triangles from each point. So now let's try to solve an example real quick. If you have 8 lines in a triangle, and you have 5 lines meeting at point B, and 4 lines meeting at point C, how many triangles can be formed in this bigger triangle? So you're going to be using our formula. Make sure to find the total number, and then subtract out your degenerate triangles. So go ahead and try to solve that. I'll give you guys a few seconds to do that. Pause the video and try to solve it. Okay, hopefully you guys try to solve it and you guys are ready. So let's move on to our solution. So here's our solution for the exam problem. First, find the total number of triangles and degenerate triangles. So our total number of triangles, it's the first one. N is equal to 8, choose 3, which is equal to 56. So there's 56 total triangles here. Now we need to find the degenerate ones. First, let's calculate it for point B. At point B, there's 5 lines there that are meeting there. And again, you have to do it over 3 because you're always going to have 3 different lines that form a triangle. So it's going to be 5, choose 3, which is equal to 10. So 10 degenerate triangles at point B. Now, from N, now you're going to have to go to point C. For point C, you're going to do the same thing, but you're going to only have 4 lines meeting there. So it's going to be 4, choose 3, which is equal to 4 degenerate triangles there. So we have 14 degenerate triangles in total, 10 plus 4. Now we simply subtract this from 56 to get 42 triangles total that are not degenerate. Again, I got all my values from a problem. The problem told us that we had 8 total lines, 5 lines at point B and 4 lines at point C. So based on that, it was pretty simple to solve it. We just needed to plug it into our formula. Okay, so now let's move on to triangulating an n-gon. So what this means is if you have a convex n-gon, and n-gon has n sides, and if you pick one of these vertex and then connect it to all the other vertices, you can find t subscript n ways to triangulate this n-gon using n minus 3 internal diagonals. So basically it's the triangles that you can divide this n-gon into based on connection of vertices and diagonals. So here are some formulas that we're going to need. First, t subscript n, so this is the number of ways to triangulate, is going to be equal to c n minus 2. So c subscript n minus 2. So what this basically means is we're going to have our c and our n minus 2. N is going to be the number of sides. So we're going to find c of the number of sides minus 2. So if it was 5 sides, then it would be c of 3. And based on that, we can plug it into another formula I'll be going over shortly. Now our t of n, we can also calculate it by finding t of n plus 1, which is going to be 1 over n into 2n minus 2, choose n minus 1. So to find the number of ways to triangulate, if we do t of n plus 1, we can plug it into this formula, and that way we can find the number of ways to triangulate. Or you could use the c of n minus 2, and then you can plug it into this formula. C of n is equal to 1 over n plus 1, 2n, choose n. So I personally like to use the c of n formula, that's easier for me, but if you like the t n plus 1 formula, go ahead and use that. But for the c n formula, what you would do is you would plug in your n here to find c of a number, then plug it into this formula to find 1 over n plus 1, 2n, choose n. So we'll be doing an exam problem with this shortly, so stay tuned for that. But that's how we would simply find the number of ways to triangulate an n-gon. So take a screenshot here if you need one of the different formulas. Okay, so let's go into a SAM problem. A vertex of a convex hexagon is connected with the other 5 vertices. What is the number of ways of triangulating? Okay, so note on the pertinent info. There's 6 sides, and you know this. So based on that, it's pretty easy to solve all the rest if you plug it into the right formula. So go ahead, pause the video, and try to solve this one. Okay, hopefully you guys did that. Let's go into the solution. So apply the formula for a hexagon with 6 sides. So t of 6 is going to be equal to c of 6 minus 2, which is c of 4, which is 1 over 4 plus 1 into 2 times 4, choose 4. So again, I simply just plug it into this formula. So if you are a little confused, go back and look at the formula, and it'll be pretty simple what I'm doing. So I'm just plugging it in here, which is going to be 1 over 4 plus 1, so 1/5, into 8, choose 4. And when I solve that out, I'm going to get 14. That means there are 14 ways to triangulate in this hexagon. Okay, so now we need to move on to counting rectangles and squares, our last topic of the day. So for an m times n rectangle, the total number of rectangles is going to be n is equal to m plus 1, choose 2, times n plus 1, choose 2. So again, this is in a rectangle with m times n, and this is the total number of rectangles you can form in this bigger triangle, or in the bigger rectangle, sorry. Now, the number of 1 times 2 rectangles, so the number of rectangles with 1 as your length and 2 as your width is going to be m times n minus 1 plus n into m minus 1. Now, the number of 1 times length rectangles, so here there's just a random number L, so any length that you have, that's going to be m times n minus L minus 1 plus n into m minus L minus 1. So this is just the ways to calculate when they're asking you, I want you to find how many 1 times L rectangles there are in this bigger rectangle. And the number of S times L. So again, S and L here are your 2 variables. If you're just given the number of 4 times 6 triangles or 4 times 6 rectangles in this, then you would just use this formula. M minus L minus 1 times N minus S minus 1 plus n minus l minus 1 times m minus s minus 1. So you're probably noticing some similarities between the formulas, so try to use this to help you remember the formulas better. But again, this is just a number of ways that you can find these different triangles or rectangles. So we went over triangles before, but now we're into rectangles. So the number of rectangles you can find in this bigger rectangle given these values. Okay, so counting squares in an m times n rectangle. For the situation with m is greater than or equal to n, where I is equal to m minus n, we have this formula. So if we want to count the number of squares in an m times n rectangle, then what we would do is n is equal to m times n plus m minus 1 times n minus 1 plus so on until you get m minus I times 1. And again, I is equal to your m minus n. So then we move on to m times n. So we just keep going on with this formula until we get to m minus I. So after this, after m minus 1 times n minus 1, then we get to m minus 2 times n minus 2, m minus 3 times n minus 3, and so on, until we get to our I value, n times 1. Now, if m is equal to n in an m times n squared grid, our formula is m squared plus m minus 1 squared plus m minus 2 squared, so on, till 1 squared. And again, we keep going until we get this I value, m minus n. Okay, so let's move on. Including a new variable. Oh wait, I just want to mention one more thing on this one. So as you can see, m is equal to n, so your I value would actually be 0, so you wouldn't keep going to your 0 value, you just keep going till your m value in this case. So you just keep going with this formula till you get maybe m equal to 5, and your minus here is also equal to 5, so 5 minus 5. At that point, you do plus 1 squared. Okay, so if we have an n times n array of points, where n is the number of dots in a row or column, and we want to find how many squares have all 4 vertices, then we use this formula. N squared into n squared minus 1 over 12. So again, this is when we have an array of points. So we have a bunch of points, and n is the number of dots in a row or column, and we want to find how many squares have all 4 vertices from the array. So how many squares can we form using this grid? Then we use this formula. So for how many different sized squares are there in an n times n array? Well, this is going to be where n is the number of dots in a row for an n times n array. Then it's going to be the floor function of n minus 1 into n plus 3 over 4. Again, the floor function, you're finding the integer that's smaller than it, but it's the greatest integer possible that's smaller than that value. So here, again, we're just given this array, and we're trying to find how many different size squares there are, how many rectangles we can form using this array. Okay, so now we're going to have a few more theorems and tables, and we'll be done soon. So for an n times n array of points, the number of squares created by slopes is equal to the number of all squares in an n minus 1 times n minus 1 array of points. So that's a theorem you want to know. It can be helpful sometimes. So if I'm given this array of points with n times n, so like 5 times 5, that's our columns, number of columns, and number of rows. The number of squares kind of is slopes. So like the slope is going to be an inclined square. So the number of inclined squares that I can create is going to be the same number of squares in an n minus 1 times n minus 1 array of points. So sometimes they'll ask you how many L times L squares are there in an M times N square. So L times L squared, well, L times L, it can just be any value. It could be 5, it could be 4. And if they ask how many of those are there in a bigger M times N square, our formula is M minus L minus 1 squared. So here's a little table. If based on our points and based on what they're asking us, we can calculate how many squares there'd be. So if we're given, if they ask like how many 2 times 2 squares are there, or in a square of 2 times 2, if we have an array of 2 times 2, how many non-inclined squares are there? There's 1. There's 0 inclined squares, and our total is 1. And so on. As you can see, I just filled out this table. So for a 3 times 3 array, we have 5 non-inclined squares and 1 inclined square, so 6 total squares. For a 4 times 4 array, we have 14 non-inclined squares, 6 inclined squares, so 20 total squares. For a 5 times 5 array, we have 30 non-inclined squares, 20 inclined squares, 50 total squares. So as you can see, Basically, we're just trying to calculate the number of different squares we can form in this array of points with the same number of rows and same number of columns. Okay, and finally, we're going to try to apply this for a rectangular solid. So right now we've been going with 2D shapes. Now we're going to move to 3D. So the total number of rectangular solids. So if we're trying to make small rectangular solids in a bigger rectangular solid with the dimensions m times n times r, then we use the formula m plus 1 choose 2 times n plus 1 choose 2 times r plus 1 choose 2. And that's how we find the total number of rectangular solids in this larger solid. And the formula for the number of cubes in the same large rectangular solid, well, that's m times n times r plus m minus 1 times n minus 1 times r minus 1 plus m minus 2 times n minus 2 times r minus 2, and so on till we get this I. So m minus I until we get to j. So j would be like your n minus r value. So r minus j times 1. Again, this one is one of those where you just keep going until you hit this I and j value. Okay, so I'm going to stay on the slide for a second in case you want to quickly take a screenshot of these formulas, and we can move on. Okay, so final formulas for counting rectangles and squares. If they ask you how many small rectangular prisms are there, and in this bigger solid, you use the following formula: m times n times r minus 1 plus m times n minus 1 times r plus m minus 1 times n times r. And you'll see that this is going to be very similar for the other ones too. And this is if they're asking you how many 1 times 1 times 2 small rectangular prisms. For how many 1 times 1 times 3 small rectangular prisms, it's going to be the same formula, except I'm going to be doing r minus 2, n minus 1, m minus 2. So basically, I've simply changed my r minus 2 and my m minus 2 from m minus 1 and r minus 1. And based on that small change, I'm trying to calculate how many 1 times 1 times 3 small rectangular prisms there are. So again, if you know one formula, it's pretty easy to find the other based on the pattern you can see. Okay, so here's our sample problem. In a 5 times 5 squares, that means that there's 5 rows, 5 columns. How many 1 times 2 rectangles are there? So how many rectangles are there with 1 over, so basically 1 rows and 2 columns. So let's try to solve that. So our solution is going to be n is equal to m times n minus 1 plus n m minus 1. So this is the formula we're going to be using in this case. Capital N is equal to m times n minus 1 plus n into m minus 1. And when we plug in our values here, we're going to have 5 times 5 minus 1 plus 5 into 5 minus 1, and that's going to be equal to 40 in the end. That means that there's 41 times 2 rectangles in our solid. So again, we simply found our m and n values because we already know that they're both 5, and then when we do the subtraction here, we got 40. There's 41 times 2 rectangles. Okay guys, thanks for watching. Please like and subscribe if you enjoyed this video. Leave a comment with any questions you have, and I'll see you guys in the next one. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramattercode.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!